All right, so for a first example here, this is just a crate sliding on the ground, but we are treating this, we've done problems exactly like this before, treating them as particles, but this one's going to be treated as a rigid body, which means that ultimately it is free. It could rotate about about any point, but we are treating it as free to rotate. So it's possible that as you apply force P at some upward distance, this whole thing could just rotate over and flip as opposed to sliding on the ground. So that's a possibility in the problem. We are given, it's a uniform 50 kilogram. That would generally mean that if we need to solve the moment of inertia, we could treat it as fully distributed. The mass is fully distributed throughout that section, but it also tells us that the CG is definitely located right in the center of the crate since it is uniform. Then we've got a coefficient of friction and an applied force. Now, looking at the free body and kinetic diagrams, on the free body, the only thing that's a little different than some things we've looked at previously is the location of the normal force is offset to one side of the CG. And the reason for that is that we're dealing with moments now. As this 600 Newton force is applied, it is going to create a moment. It's going to create a force that wants to rotate the box in that direction. Excuse me. Assuming that the box doesn't actually rotate, then that means that the resultant normal force needs to shift to sort of balance that. So if that 600 Newton force is creating a moment that's wrapping in the clockwise direction, the normal force is actually creating a moment that wraps in the other direction, and they do balance out. So we'll see that when we add this up. But what we're treating that as is the distance that the perceived normal force acts is not known. That is a variable that will solve out of the system of equations, which is quite good. In reality, if you've got a situation like this, the bottom of that box is probably going to be subjected to some sort of distributed force. You've seen that from mechanics materials, probably, maybe statics. But any distributed force has some result, and that's what we're treating in as here. So that's the way we're going to set it up. All right, so we're going to have a summation of forces in X, a summation of forces in Y, and a summation of moments about G. A moment about G, we know is going to be equal to 0 because we are assuming, and I'll just write that up here. I'm going to assume two things. I'm going to assume that it does slip. There's a possibility that 600 Newton force is not enough to actually make the crate slide, in which case, it's a static problem. But I'm assuming that it does slip and that it does not tip. So I'm assuming that this thing is sliding across the ground when subjected to that force. If those assumptions are wrong, then I'm going to get some weird signs in my results, and I'll be on the lookout for those. So we'll have mass AGX and mass AGY. And then we can write in everything we know. So in the X direction, we have the 600 Newton applied force. We have the force of friction, which is a minus 0.2 times N. Those are the only forces, and that's going to be equal to our mass, which is 50 kg, times acceleration at the CG. And since this is only sliding in the X direction, the X component of acceleration is the full acceleration as well. In Y, we're going to have NC, or I'm sorry, just N, as I'm saying, minus the weight, which mass times gravity gives us 490.5, and that is going to be equal to 0. It's not moving in the Y direction. And then the moments, this is where in the notes video we talked about despite the fact that there's no motion of rotation, the summation of moments can still give a lot of good use. And in this case, what we've got is the 600 Newton force is acting at 0.3 meters from the CG, and then of course the force of friction is acting at 0.5 meters from the CG, and then the force N is acting at distance x there. So we'll have minus 600 times 0.3 plus the normal force, it's acting at x, and then the friction force 0.2 times N, it's acting at 0.5, all equal to 0. And yeah, you just need to pick a direction to equal to be your positive there. And in this case, I'm setting that equal to, looks like we've got a positive direction in the, or no, other way, counterclockwise direction. And then X and Y are your standard directions there. All right. Now, out of that, you can solve any number of things. You got N is already going to fall straight out of it. It's just equal to 490.5 newtons. That lets you solve for X, which is 0.467 meters, and those two will let you solve for AG, which is going to be equal to 10 meters per second squared. Okay. Now those are all reasonable numbers. N came out positive, so there is a reaction there. AG is positive, so it's accelerating in the x direction. And then of particular importance there, what X is the distance N needs to be to balance the system, essentially. So you're always going to get a value for X when you solve this sort of a set of equations. But in the physical problem, if X were greater than 0.5, this distance is 0.5, then the balance point would be somewhere over here in space. What that would imply is that for this to be a balanced system, your crate would have to essentially be physically extended in that direction, or it is going to flip. So in looking at these results, getting a positive value for N indicates that it has real meaning to the problem and that it matches our assumptions. It's not flipping currently. Having an X value that is within the range where it physically makes sense to the system, that tells me that everything's good. And then pretty much I'm going to expect AG to be positive because I've only got one force pushing it. But yeah, that's all there is to that one. In general, with this type of problem, you could also study what force does it take to cause it to flip, things like that, which we may do in class next week. But for now, we'll leave this one here. All right, so here we've got a beam BD of known mass, and it's supported by two rods AB and CD of negligible mass. And since those are of negligible mass, there'd be negligible inertia as well, so we can treat this as a translating problem. In particular, since AB and CD are of the same length and geometry. So as this thing moves at velocity omega over there, the whole bar BD, it just translates to the left of the page. So it is a purely translating problem. All right, so before we do anything else, if we just look at, well, let's look at link AB here. A is a pin, of course. It's just rotating about that, and as we've seen before, if you're rotating at a constant velocity, you can view your system as a normal tangential setup like this, where yeah, I mean, that is your normal tangential system. And then down here at B, we've got, we can solve for the accelerations there. Now, since omega is constant, alpha is 0 for bar AB at least. And that means that the tangential acceleration in this little system also has to be equal to 0, but the normal acceleration, AN, is going to be equal to omega squared R. And we've got omega is, let's do it like this, AN is equal to omega squared, which is given as 6. I'll just take the direction as shown as positive. And then R is 0.5, so we've got 36 over 2, or 18 meters per second squared. Now, just for reference, if I was to do the same thing over here at the other rod, I'd get the same result for that. So that's going to be the acceleration actually at B and D, because it's the same geometry moving at the same speed. That actually as well, if both of those points are moving in a well, I'll come back to that in a bit. Let me draw out a free body diagram for the bar first. The beam itself. So this will be BD. I've solved the accelerations at B and D. And I'm going to be looking for some values at G. Okay, so in terms of forces, I'll definitely have the weight of the object. That'd be 100 kilograms. With gravity, that would be 981 newtons. And then the two forces in the rods will have to be along the rods, be T or TB and TD. They're going to be in the directions of the two rods, A, B, and CD, because that's the direction of the accelerations in those rods. Those are the only ways that it can transmit forces along the direction of acceleration. So those are your two force vectors, essentially. And so those will both be at 30 degrees off of the vertical. Now, as far as it goes, those are going to be equal in magnitude in the end, but we'll sort of prove that as we go here. Okay, so with that known, point G let's look at its accelerations here real quick. So go to red, why not? So let's put it in the same basic coordinate systems as point B and D. Now we can say, since this gets a little finicky here, but since points B and D are both accelerating in the same direction with the same magnitude, and basically that says that there is no rotation in the bar. If there's no rotation in a rigid body, then every point on the rigid body is going to have the same directions of acceleration. So that would specifically mean here that we have this AN term at G is also equal to 18 meters per second squared. Now, as far as tangential acceleration at G, we cannot say that it is 0, or at least not using the same logic that we use for B and D. We can say that B and D have no tangential acceleration because they are attached to links that have fixed points of rotation and they have a fixed rotational speed. But G is the center of the bar itself is definitely moving through some sort of geometry, but it's not necessarily a circular arc. In fact, it's not a circular arc. So we actually can't say at this coordinate system that AT is 0. So we're going to say AT at G is an unknown at this point. If it proves to be 0, that'd be great, but it's not going to. It is going to have meaningful value here. So what we can do now is write out the equations of motion based on that free body diagram and see what we can solve. So we're going to base this off of that inertial reference frame, essentially. So even though they're aligned and they're in the same kind of orientation, the reference frame on link AB is not the same reference frame as that of BD. It is centered at G and therefore tracking motion at G. So let's sum forces in the n direction. We'll go positive in the positive n direction, equal to mass times AGN. So here we've got force TB and TD. And then we've got the weight component in the normal direction is 981 times the cosine of 30. That's going to be equal to mass times acceleration. In the normal direction, we found to be 18. In the tangential direction, all we have there is the component of weight, 981 times sine 30. That's going to be equal to our mass times tangential acceleration at g. So you can see there that AGT term is definitely not going to be zero. And then if we sum the moments at g, that is definitely not rotating, so it is going to be equal to 0. We have component of TB causing a negative rotation, cos 30 times 0.4 plus TD cos 30 times 0.4. So the sine components of TB and TD, of course, those act through point G, and those can't create a moment, so they just don't factor into that in this problem. All right, so from this expression, we definitely get that TB is equal to TD. That's handy. From the second expression, we can get that AGT is equal to 4.91. And then plugging the TB-TD relationship back into the first equation, we can solve for its magnitude, and that comes out to be 1320 newtons. All right. And then as far as it goes, this one, and making this choice right here to use a normal tangential system at G, you could still work this out with an XY coordinate system based at G. You're just your summation of forces, equations of motion for X and Y would be just ever so slightly more complex than they are in the normal tangential system. So it doesn't make a lot of difference, but it can be solved either way, of course. All right, this is a pure rotation problem. It's a bar rotating about 0.0. It is hanging in space, so we will have a gravity component at the CG. It's a uniform bar, so CG will be at the center. In this case, you do have an applied moment, so that's going to factor into the summation of moment equation of motion. But the rest of the approach is pretty similar to things we've already done. So went and wrote out the free body diagram and the kinetic diagrams down here, and essentially I'm treating this as calculating accelerations directly at the CG, and since this is rotating about a fixed point, I can very directly treat it as a normal tangential system with n in that sort of direction and t down there. So in terms of our kinetic diagram, what that would imply is that we have, I'll just label them here, normal acceleration is m omega squared r, or I guess I could call this the inertial diagram. Let's go ahead and put the mass terms in there. Let's get rid of that, or actually let's do this, an mass times an, there we go. Omega squared rg, of course, is the normal acceleration. I just needed that mass in there. And then down here, our tangential acceleration times mass is equal to mass alpha rg. And then we also have to have the actual Ig alpha term for the summation of moment equation. And essentially from there, we've got everything to start plugging in and solving. And what we're solving for in this case is the value for alpha. and the two reaction forces, which are at O over here, and they're just given OT and ON. Those are reaction forces there, so that's what we're solving for. So, and the coordinate system that we're using there essentially is going to be the normal tangential as defined at the CG. So that system just aligns to that. So if we sum for forces in the normal direction, and based on our diagram, that's going to be our positive direction, is equal to m omega squared rg. We've got ON is in the positive direction, no other forces, so that's going to be equal to 20 mass. Omega is known as 5, and Rg is also known as 1.5, half the bar length. So that lets us solve for ON directly as 750 newtons. Do the same process in the tangential direction. In this case, downward is positive. So since downward is positive, OT is negative in the summation of forces. And then we've got a positive weight term, 20 times gravity, is equal to mass times alpha times Rg, which is still 1.5. So there we got two unknowns, so we cannot solve for it directly, but we've got one more equation to apply, so that should take care of that. So if we sum moments at CG is equal to moment of inertia, mass moment of inertia at the CG times alpha, and in this case clockwise is positive. So we've got OT acting at 1.5 meters from the CG. Remember, I'm summing moments at the CG. I've got the 60 Newton meter applied force. Remember, when you've got an applied moment, its location doesn't really matter. You can apply that moment anywhere on a rigid body, and when you sum moments, it's just a moment. Its magnitude doesn't change based on position, so that's all we have there. And that's going to be equal to I alpha, which I for a slender rod is going to be 1 over 12 times the mass times its length squared. That would be the Ig term, and that multiplies by alpha. So now we can solve the last two equations there together for alpha and OT, and then from that we get OT is 19.05, and our alpha term is 5.9 radians per second squared. Okay, here we have a problem that's not too dissimilar to the previous problem. However, in the previous problem, you were given enough conditions at its current state to solve for the rest of the information at its current state. In this one, you're given that it's released from rest when theta is equal to 0, and it wants you to find reactions when theta is equal to 90. In other words, when the bar is hanging vertically in space. So real quick, since it's going to rotate through angle theta, and the only inertial component acting on it, it would be the weight. That component of weight is going to, as it reacts through theta, and we'll show this in a second, the component of weight that goes into the, up here we can just call it the x and the y directions, it's going to change as the bar rotates, of course. So it's not constant is another way of putting it. The alpha term's not going to be constant, and that means that theta is not constant, or a change in theta is not constant. So we are going to have to do a little bit of integration in this one, which can be a little misleading because the only acceleration that you clearly have is gravity, which is often treated as a constant, but when you've got the inertial effects in play, that's no longer going to be purely the case. And even if, in this case, if there was no inertial effect, you'd still have to integrate. But we'll set it up and show how to go through it. All right, so we've got moment of inertia about point A, which is the end of the bar. We are going to use that information, and that's going to make the solution a little easier than we could solve this for IG, work it that way too, but solving it about point A is going to save us some time. So we've got a normal tangential coordinate system applied as such, and the reactions are given here as AT and AN, with their directions just shown in the positives of this coordinate system over here. So again, a kind of a free body diagram and an inertial or kinetic diagram. We kind of call those interchangeably. Okay, so same sort of deal, though. We're going to sum forces in normal, tangential, and then we're going to sum moments. So in the normal direction, we've got m omega squared rg. In the tangential direction, we're going to have m alpha rg. That way is positive. And our moments will be, as I mentioned, at point A in this case, as opposed to the CG. So that's going to be moment of inertia at A times alpha. And then plugging in what we have. I'm keeping everything in terms of variables for the moment. We'll have, in this case, the reaction force AN minus mg cos theta is equal to m omega squared times L over 2. That'd be the RG term, would be the L over 2. And we've got AT plus mg sine theta is equal to mass times alpha times L over 2. Then our moments here, we're going to have weight itself is just going to be mg cos theta is causing a moment at length L over 2 is equal to, our inertial term is 1/3 ml squared times alpha. Now this is another one where sort of orienting the normal tangential system to the bar itself just makes the components a little easier. I could also solve this in an XY system that's in a kind of traditional orthogonal sense, but the normal tangential system will make it a little more straightforward. Okay, so from that point we've got a few ways of going about it, but essentially for angle theta we've got the AN and AT are unknowns. Omega is unknown, and alpha is also unknown. And then alpha is not constant because it does depend on the rotation of the bar. If we look at that last equation there, where we've got alpha right there, L is constant, M is constant. So the only variable there is theta, and theta is not constant. So since theta is not constant, alpha is not either. So that's where we kind of prove that we have to integrate this equation. And the form that can be used here is going to be omega times d omega is equal to alpha times d theta. This is very similar to your v dv is equal to a ds type of equation in the linear sense. All right, so in setting this up, I can take, let's see here, from, essentially what I'm going to do is write out this expression, the whole thing, in terms of alpha. And of course, a lot of the terms in there cancel out nicely when I do that. So what I get there is that, let's see, the mass terms cancel, one of the length terms cancels, and let's see, we got 3 is going to come over, 3/2 is going to be 1.5. G stays. Got one L term left, and the cos theta. And I believe that's right. And that's going to be equal to alpha. So that can go into our expression there, and we get omega d omega is equal to 1.5 G over L cos theta times d theta. And then we can integrate, and we are releasing this from rest. So we're starting out with a speed of 0. We end up at some future speed, omega. And then on the other side, we're going from 0 to 90 degrees. Taking that integration and plugging in the limits as they are stated there, we get omega squared is equal to 3G over L. And from there, that can go back up into our AN equations, or our equation of motion in the n direction. Right there, we got the omega square term right there. And when I do that, it's fully solvable. And what I get when I basically sub everything in and work through it, I'm going to get AN is equal to 2.5 mg. Never had the mass of the bar, so can't really do anything there. AT is actually going to come out to be 0 because alpha is going to be 0. So all of that just to take the cosine of 90 and say that it's 0 basically. But yeah, that ends up being the final solution there. And the main thing out of all this is that you're getting to this expression right here, which is a functional relationship between theta and alpha. And once you have that positional equation can always be processed through that kinematic equation. So those are the kind of big takeaways from this particular problem. Okay, here we've got a wheel rolling on essentially level ground. We're given a radius of gyration here, which is another way of essentially expressing the mass moment of inertia. So I'll show the conversion there here in a second. We know that there's a moment applied to it, and we've got both a static US and a kinetic mu K term there. And we need to determine, as part of the problem essentially, is this thing slipping as it rolls or is it not? It's not a known thing at the moment. So as far as the radius of gyration there, we're given it as kg is equal to 0.70 feet. And well, it's all here at the bottom of the page now that I look. This expression here is your conversion where kg is the radius of gyration. And it's literally, it's not introducing any new terms because radius of gyration already has a mass in it. It's basically just simplifying, if you want to look at it that way, the units. And often in like structural steel catalogs and things of that nature, they'll express radius of gyration because they're typically they're typically easier units to deal with, just depending on the mass system. But it's a really common thing in civil structural calculations to use radius of gyration. But if you do see it in any other problems, I try to avoid it just because it's the less common expression in mechanical work. But if you see it, you've got the conversion there. It's always known. And incidentally, they go ahead and carry out the mass moment of inertia calculation for us. That's going to be nice here in a second. So on a free body diagram, let's I'll redraw it here, I suppose. And we're going to have the weight which is given in the problem statement as 50 pounds. We're going to have a normal reaction, and then there's going to be a friction force as well. This one has an applied moment to it, which is 35 foot-pounds. It's a B, and yeah, that should be everything for the free body. And then our little kinetic diagram over here will just put everything in the XY system for this one, since it's not, well, it's pretty much only moving in the X direction, so that should be okay. Our only acceleration is in the X direction, and then we do have the alpha term since the thing is rotating. So this is creeping into general plane motion because this is simultaneously rotating and translating at the same time. If you recall general plane motion, you can always basically, if you can figure out components of rotation and translation separately, you can just add them together to get the plane motion. And that's kind of what we're doing here. But let's scroll down and write out what we can for equations of motion. So we'll start with the summation of forces in X. Mass times acceleration of gravity, or acceleration at the center of gravity, X. And we've got our force of friction is equal to the mass, which will be 50 over 32.2 times an acceleration term, which we do not know yet. Forces in the y direction. We'll just have our normal force minus the weight, 0, so that tells us the normal force is just the weight. And then lastly, our summation of moments about the CG. And we've got clockwise is positive. So there we're going to have we've got the applied moment of 35. That one is in the clockwise direction, so it's positive. The force of friction acts at 1.25 feet. The radius of the object. Gravity acts, of course, through the point of gravity, so it cannot create a moment. And then the normal force also acts through the point that we're summing moments at, G, so it cannot create a moment. So that's everything. And then we have the term for moment of inertia and alpha. Okay, so out of that, we do have, what do we have? Force of friction, acceleration, normal force, and alpha are all unknowns. So we do have to come up with some relationship there. And of course, through kinetics, we know that AG should be equal to R alpha. So that, well, actually, let's be clear about something here. Let's solve this by assuming no slip. Let's do that first. And in that scenario, there would be a direct relationship between AG and alpha, and it would be based on that radius there. And that lets us say AG is equal to R times alpha. So that would be 1.25 times alpha is equal to AG. So that's just straight general plane motion kinematics there, essentially. And at that point, we've got 4 expressions with 4 unknowns, and we can solve for those. I'll just give you the results of that. Is we have I've been calling it NA, so let's just do that. The normal reaction NA is 50 pounds. FA, that one I have force of friction, FF, is equal to 21.3 pounds. alpha is equal to 11 radians per second squared, and then AG is equal to 13.7 feet per second squared. Now, that was looking at this in terms of what's the solution if the problem does not slip, if the cylinder does not slip. But we've reached a point where we can figure out if the cylinder is going to slip or not, because our limit of slip, we need the force of friction to be less than or equal to the static coefficient of friction times normal force. Okay. So the static coefficient was 0.3, our normal force is 50, mu times 50, 0.3 times 50 rather, that's 15. And we calculated force friction of 21.3, so that is definitely not less than the limit of slip. So that implies that this is slipping. So that's that relationship there, based on the friction that we calculated, means that the object is slipping. So we need to go back and factor that in to calculate some final values here. So let's rework a few things. If it was slipping, in this case, my force of friction becomes mu k. I use the static value of friction as if it was not slipping. When I know it's slipping, I use the dynamic value or kinetic value. And we get out of that force of friction should actually be equal to 0.25 times the normal force. And everything else is essentially the same solution there. You can go back and work through everything, set the equations up with that change in mind, and now you are solving 1, 2, and 3 along with sort of the new, well, let's call it 5, and that gives you a few different values. The normal reaction is still the same, it's 50 pounds. Our force A, or our force of friction, now is 12.5. It's just at the limit always, because once it starts sliding, it's just sliding. There's nothing to change the value. And then alpha becomes quite a lot larger. And our linear acceleration becomes slightly smaller. So what that would sort of imply, if I sort of look at the accelerations next to each other or in comparison to each other for the two cases, once it starts slipping, that means that it is rolling faster than it is sliding, essentially. So that kind of makes sense that your alpha term goes up. At the same time, more of the impulse or energy or whatever you want to call it that is causing motion is going into causing the object to rotate. And so its translational acceleration drops a little bit. There's nothing much more to learn from that, but it's just, it does make sense sort of intuitively that if the thing is slipping as it rolls, it's going to be moving, rotating either faster or slower than it would otherwise, but in this case it's going to be faster because the force of friction is too low to prevent slip. Okay, here we've got a horizontal bar of known mass being supported by two cables, and then at some instant one of the cables is cut, and essentially immediately after that the bar would start to drop, and since it's still supported by the other cable, it's going to rotate as it falls. And we're looking for the tension in the remaining cord and the angular acceleration after AC is cut. And these sorts of things are pretty common in where you have what would be called a fail-safe design, which is essentially both of those cables are holding that bar up, but if one of them fails, does that mean the whole thing's going to drop, or does the remaining cable have enough strength to at least keep it from falling all the way? So this is a pretty typical kind of calculation in aerospace, and then just even structures, civil structures, buildings, things like that. Anyway, if we look at the free body diagram, we're going to have not a lot going on, but a few things. We're going to have the tension in this remaining cable, which we'll call the tension at B. And then there will be the weight term. And that's pretty much it for the free body diagram. And then for the kinetic diagram, we will have, let's see, I guess I'll just draw it on the part again. Why not? Well, there's a few ways we can look at this. But essentially, a B can have an acceleration. You have acceleration of the CG in the y direction, acceleration of the CG in the x direction, and then we also can have an alpha term applied to that. And then I'll put it off to the side that omega is 0, because this is happening immediately before motion has started. And when you see those the word immediately in there, something that's been at rest, but then something imposes motion on it, right before any velocity is generated, there has to be an acceleration. You can't go from rest to a non-zero velocity without an acceleration. So we would expect the velocity to be 0, but not the angular acceleration. So we should get a result for that when we solve for it. Okay, this one's got a little bit of kinematics as well as a little bit of kinetics, and let's just start with the kinematics for this one. So and we can treat this with the sort of relative acceleration equation that we've used when we were looking at rigid body kinematics, and that one stated, or we're going to write it out as AG is equal to AB plus alpha crossed with RG is viewed from B minus omega squared RGB. Of course, we're in vector space now, so let me add that back in everywhere appropriate. Okay, now some of these are going to be 0, but some of them we will be able to write out solutions for otherwise. Now, as far as B goes, let me just come back up here. I've drawn its acceleration as in the x direction. We've seen a number of times things sort of rotating about a fixed point, which you can think of BD as that they're going to have a normal acceleration. But because this thing hasn't moved yet, there is no velocity. If there is no velocity in the problem, then the normal acceleration term, whether you're thinking of it as omega squared r in this case, there is no omega yet, so that's just going to be 0, which is why it does not show up on the kinetic diagram. And then as we write that out, we're going to have, let's see here, lost my place. Let's see, there we go. Okay, the acceleration of G is going to be initially minus AG y in the j direction is equal to AB. We just said that's only in the I direction, plus alpha, which is in the k direction, crossed with a minus 1.5 I for the r vector. And then our omega term is 0, so that term drops out. Now, there is, at G, there is, well, I guess maybe I should have started with kinetics on this one, but we'll get to it here in a second. Let me actually just put in AGX in the I direction over here. Okay. So out of this, the acceleration terms are basically all unknown at this initial point, so we can't do a whole lot with it. But we're going to get to, well, I can do this real quick though. We can do AGX in I minus AGY in J is equal to ABI plus, or that's actually minus there with the cross product, minus 1.5 alpha in J. All right, then we can come back to equations of motion in the kinetic solution. And there we're going to have a summation of forces in X. And I'll take to the right to be positive is equal to M AGX. There are no forces in the X direction, which of course is going to say AGX component is 0. So that's what I was kind of stammering about there, is that that X component has got to go to 0 regardless. And in the Y direction, summation of forces in Y with vertical upward positive M AGY. Now we've got the tension, TB, minus the weight, 50 times 9.81, is equal to the mass times AGY. And that's actually going to be a minus there. And the reason for that is, I remember I want to match my diagrams as I write out my equation. So I drew AGY to be downward positive, but my coordinate system says that upward is positive. So that generates that negative sign right there. And lastly, we'll have a summation of moments about the CG is equal to the mass moment of inertia at the CG times alpha. And there's not a lot going on there. The weight acts through the CG, so the only remaining force to cause a moment is the tension in B. It's acting at a distance of 1.5 meters. And then our equation for the mass moment of inertia for this case will be 1/12 times the mass times the length of the bar squared times alpha. Okay. So from there, what do we want to do? Let's go back to the kinematics real quick, and that's essentially what we have there. And if I split that into components, what I'm going to get is 0 is equal to ABI. So essentially no acceleration at B whatsoever. We've proven that. And then we've got AGY in the J direction is equal to 1.5 times alpha. So in that case, we've got TB, AGY, and alpha as unknowns, and then that kinematic expression gives us the bridge to solve 3 equations with 3 unknowns, essentially. And when we do that, as the last step, alpha comes out to be 4.91 radians per second squared. The tension in cable B is equal to 123 newtons. And the acceleration of the CG is only in the Y direction, and it has a value of 7.36 meters per second squared.